The chemistry of metal compounds with silicon-containing ligands have been increasing over the years. Several groups around the world have developed important ligand systems for metal complexation. Owing to the chelate effect, these molecules are stable and provide the basis for ligand design in catalysis. The importance of the silicon atom to be incorporated as part of the resulting complexes is mainly due to the excellent sigma donor ability combined with its considerably high trans influence or effect. These features allow the metal center to be electron-rich, enabling them to activate inert substrates. Silicon, placed at the third period of the periodic table, possesses properties between carbon and their heavier analogues. The silicon atom, with an electronegativity value of 1.9 in the Pauling scale, it is more electropositive than carbon, hydrogen, and many transition metals. Silicon present in many products we use in our day. The research of bioactive compounds incorporating silicon atoms into their structures is one of the main research areas around the world. Hence, the importance of the synthesis of molecular entities capable of inserting silyl fragments into organic cores. For many bonds which incorporate silicon, their energy dissociation values show that silicon-oxygen, silicon-fluorine and silicon-chlorine bonds are higher in energy, while silicon-hydrogen, silicon-carbon, silicon-silicon and silicon-iodine are among the lowest in energy. Silicon-silicon bonds are non-polarized sigma bonds, which possesses a mean bond dissociation energy value of circa 300 kJ per mole, around 43 kJ per mole less than a silicon-hydrogen bond. Bond distance values for silicon-silicon bonds are found between 235.8 and 237.2 picometers, around 80 picometers longer than in single carbon-carbon bonds. This picture shows the steric effect of substituents on some disilane compounds, with elongation or compression of the silicon-silicon bonds. It is observed that compounds like hexachous disilane have exceptionally elongated silicon-silicon bonds, while compounds like disilane or hexamethyldisilane are considerably short. The silicon-silicon bond is moderately reactive towards group 1 metals. Silicon-silicon dissociation in these systems is considered to proceed via electronic transfer of the metal center to the low-energy sigma molecular orbitals of the disilane bond, which results in an elongation of the bond. The pi contribution between silicon and aryl groups strengthens the silicon-carbon bond as seen in the picture, thus promoting specific silicon-silicon bond cleavage where metallic lithium is used. The silicon-hydrogen bond is a polarized sigma bond which is more basic than hydrogen-hydrogen and silicon-silicon, hence, it behaves as a better electron donor group. Hydrosilanes, with general formula, are versatile starting reagents, useful for the generation of silyl metal complexes. Hydrosilanes can interact with metals in many possible ways, from non-classical bonds as in sigma complexes, up to fully broken silicon-hydrogen bond to form silyl compounds. The silicon-hydrogen bond distance is generally between 146 and 149 picometers, about 38 picometers more than for a carbon-hydrogen bond. The silicon-hydrogen bond, depending on the substituents attached to silicon, presents a wide range of dissociation energies. For example, for the series of hydrosilanes, a decrease in the bond dissociation energy is observed. Hydrosilanes and disilanes react with a wide range of transition metal precursors. In general, the mechanism by which silylation products are generated is through the oxidative addition of the silicon-silicon or silicon-hydrogen bond towards a metal center. The oxidative addition reactions of hydrosilanes are much more favorable than those of hydrocarbons and normally occur at room temperature. The silicon-hydrogen bond broke up on reaction with the rhodium metal center. Therefore, rhodium increases its +1 oxidation state to the +3 state. The reactivity of metal precursors that have organic fragments, MR, frequently results in their elimination in the form of hydrocarbon RH after the oxidative addition of hydrosilane. The silicon-hydrogen bond broke up on reaction with the W metal center. Subsequent elimination of methane favors the reaction. Reactions of hydrosilanes with metals can form species of complex nature, especially when primary and secondary hydrosilanes are used. A synthetic route that normally generates direct silylation products results from the oxidative addition of CC bonds towards metals that are in low oxidation states, mainly late transition metals, such as those of the platinum group. The silicon-silicon bond is easily broken by electron-rich metals. Furthermore, silicon atoms have electronegative substituents, allowing them to be more reactive. As stated above, the chemistry of hydrosilanes and disilanes is vast. However, an understanding of the properties of these compounds and their trends associated with the change of substituents around the silicon atom remains poorly explored. The efforts published in the literature highlight the importance of the research of hydrosilanes and disilanes as important raw materials in the elaboration of complex molecules with high value for industry, academia, among others.